Now that we have explored the use of the inequalities to bound probabilities, we need to turn to asymptotic results. Specifically, we will explore results related to the asymptotic behavior of the sample mean. And because we're dealing with asymptotic behaviors of the sample mean, what we need to do is recall what's going on with the sample mean and derive a couple of results. So first of all, let's think about the definition of the sample mean that we learned about back in the chapter on moment generating functions. So if we let x1 to xn be IID random variables with expectation of each of those x's equal to mu and variance of each of those equal to sigma squared, then we'll define the sample mean to be x bar sub n, which is equal to 1 over n times the sum from I equals 1 to n of the xi's. So that's our sample mean. Based on our knowledge of expectation and variance, we can easily derive the expectation and variance of x bar as just a simple application. So let's start with the expected value of the sample mean. Well, let's first substitute in the definition. So that's the expected value of 1 over n times the sum from 1 to n of the xi's. And we know that we can rewrite that by pulling out our constant from the expected value. And then just for clarity, let's rewrite the summation notation in terms of an actual sum. I know that might seem a little bit like overkill, but it might help some folks see what's going on. And then we know that expectation is linear, so we can break up the expected values that we're dealing with here, right? And so we get this result. That right now we have the expectation of the sample mean is equal to 1 over n times the sum of the expected values, but now we need to realize that things are IID, right? So because things are IID, notice that all of these expected values are equal to the expected value of x1. So we have n of these elements in our sum, and so this is going to be n times the expected value of x1. And we know what that expected value is because the expected value is mu as defined above, and so we get 1 over n times n mu, which simplifies down to mu. And so this is a very nice property of the sample mean, especially because if the mean of our random variable is mu, we know that we can then estimate the mean using the sample mean, and that's what we would call an unbiased estimator in statistics because the expectation is equal to the mean that we think it should be. Now let's move on and look at the variance of the sample mean. And so again, let's start off by looking just at an expanded definition of the sample mean. And then we know we can pull out our constant and square it from the variance. And then we have the variance still of a sum. Now remember that these random variables are independent, so because the xi's are independent, we can rewrite this variance as the sum of the variances of each of those xi's, again because they're independent, so we know that the covariance between all of those are 0. And now notice that the variance for each xi is exactly the same. It's going to be sigma squared, so we get 1 over n squared times n sigma squared, which yields a variance of sigma squared divided by n. And so these two results, that the expectation of the sample mean is equal to mu, or the mean of a single xi, and that the variance of the sample mean is equal to sigma squared divided by n, are extremely important results, and they'll keep popping up over and over again, so it is worth really working through those and understanding that. And While the expectation and variance are very good to know, they don't tell us everything about the behavior of the sample mean that we might be interested in. So there are still some outstanding questions, such as 1. When can we be confident that the sample mean is close to mu? So we know that on average the sample mean will be mu, but that doesn't talk about what's happening in each individual case where we're estimating this sample mean and in an effort to estimate the population mean. So when is it a good approximation? How many samples do we need? The second question is, well, what's the distribution of the sample mean? So we know what the expectation and variance are, but we still know that very little. We don't know if it's a unimodal distribution. We don't know if it's a bimodal distribution. We don't know how many outliers there are really. So we need more information here. And in order to answer these questions, we're going to need to appeal to what we call the limit laws. And we have two basic limit laws. We have the law of large numbers, and we have the central limit theorem. Both are very famous results that you're probably familiar with, but we need to investigate these a little bit more deeply for this course. So to begin, let's start with the law of large numbers. Okay, and there are actually two laws of large numbers, and both of them are going to shed light on the first question. And that first question, remember, was when can we actually be confident that we have a good estimator of mu when we're close to where we actually want to be. And so we have two laws of large numbers, which might seem a little bit odd, but we'll talk through what each of them says. And one is called the weak law, and the other is the strong. We'll discuss the weak first, so that we're going in ascending order of strength. So here, let's just write down what the law of large numbers says in terms of the weak law. So this is the weak law of large numbers. And because we're going to be writing the law of large numbers so often, I abbreviate the law of large numbers LLN. So the weak law is then WLLN. And what this says is that for some sequence of random variables, so we have some infinite sequence of random variables, I'm just going to let that be x1, x2, so on and so forth, and that's going to be a sequence of IID random variables with expectation given by mu, so this is going to be true throughout the entire lecture today, and variance equal to sigma squared, and we're going to need to make an additional assumption about the variance, not just that it's equal to sigma squared, but that sigma squared is finite. Okay, so now we have our assumptions here, so remember that this says that we actually have a mean and we actually have a variance for this distribution, or for the distribution of these random variables. And then what the law of large numbers says, well, then for all epsilon greater than 0, the limit as n approaches infinity of the probability of the absolute value of the sample mean minus the population mean being less than epsilon is equal to 1. And so that's the statement. We're going to first prove it, and then I'm going to talk about what this actually says in intuition. But let's just first make sure that this result is in fact true. And I'll go to a new page here just for clarity. And so first of all, we're going to need to let epsilon be greater than 0. Okay, and remember what we're shooting for. We're trying to establish that the probability that the absolute value of x bar and minus mu is less than epsilon is equal to 1. Okay, so it's actually easiest to establish this proof to start with something that we're not quite looking for, but is easy to rearrange into what we're looking for. So this proof starts by looking at the probability that the absolute value, the absolute distance between the sample mean and not epsilon, but mu being greater than epsilon, and so that's where we want to go. And so if you think about that, well, we certainly want this to go to 0 in order for what we want to prove. So let's first of all think about where we can go from here. Now, we have two choices about where we can go. We can either use Markov's inequality or we could use Chebyshev's inequality. I'm going to show you the way that I've seen using Markov's inequality first, and there'll be a proof later on where we can use Chebyshev's right away, just so that we have some practice using both inequalities and seeing the results here. So if we expand this out so we can use Markov's, what we're going to do is get rid of that absolute value. So we're just going to square both sides of this inequality. And then what we're going to do is apply Markov's inequality. And so that's going to say that this probability here is less than or equal to the expected value of the left side of the original inequality divided by that right side. Okay, and so then what you're going to notice is that the expected value of the squared quantity x bar minus mu, well, that's just equal to the variance of x bar n by definition, and so we can just rewrite this as the variance of x bar n divided by epsilon squared. And notice that you could have jumped right here by Chebyshev's inequality, and that's absolutely fine. I just wanted to show you a couple ways that you can work with this. And so now simplifying this, we know that the variance of x bar n is equal to sigma squared divided by n, and that's going to be divided by epsilon squared. So then we just see this is sigma squared divided by n epsilon squared. So now we need to start tackling the original problem that we'd outlined for ourselves. So let's write down what our original target was, and that's the probability that this absolute distance between the sample mean and the population mean is less than epsilon. And then we'll rewrite that just in so we can get the probability of the inequality we derived above. So that's 1 minus the probability of that absolute distance being greater than or equal to epsilon. And so we then know by the inequality that we've established above that this is greater than or equal to 1 minus sigma squared divided by n times epsilon squared, and then that quantity is going to go to 1 as n goes to infinity. We're not quite done because we didn't establish equality. We've only established this inequality here. So to finish this up, what we need to do is that we know that probabilities are at most 1. So the equality is then established. And so that's the proof of the weak law of large numbers. And so now we need to work on interpreting what the law of large numbers is saying, what that weak law of large numbers is saying. And so now let's just talk about remarks. And there are a number of remarks I'd like to make here. The first is what the weak law actually says. So the weak law of large numbers says that the sample mean approaches the population mean as n approaches infinity. That is, for large n, x bar n is close to mu with high probability. And so it's good to understand intuitively what this is saying. So it basically says that the sample mean is going to be close to the population mean with high probability for a large enough sample size. But what the weak law does not say, so the weak law does not say that the sample mean stays close to this population mean. And so this seems like a counterintuitive result at first, until you kind of think about a representation of what's going on. So if you think about the weak law of large numbers and the sample mean, just think about adding the number of heads flipped in a series of flips of a fair coin. And let's say you're going to flip that fair coin 1 million times. The weak law of large numbers says that the proportion of heads will be close to 1/2 with high probability, but it doesn't prevent strings of bad luck being hit that temporarily pull away the sample mean from 1/2. And so that's why the weak law of large numbers does not say that we stay close to that, because it doesn't talk at all about those strings of bad luck. We'll return to those strings for the strong law of large numbers. My third remark on the weak law of large numbers is that it also goes by another form, and that's the form of convergence we're talking about. So the weak law of large numbers discusses something we call convergence in probability. Okay, and so what that says is that if you look back at the definition of what's going on here in the weak law of large numbers, the limit as n goes to infinity of the probability of the absolute distance between a random variable and its mean being less than epsilon equaling 1, well, that's what we call convergence in probability. So this is also stated as x bar n converges in probability to mu. And so this is just a mode of convergence that we have here. And the notation that we use in probability and statistics for this mode of convergence is we have a random variable, and let's just use the sample mean for this example, and then we say it converges in probability, so we just place a p over that as n approaches infinity. So it's pretty simplistic notation and nothing really that new that you have to work with. And then my fourth comment here is a pointer towards statistics. So, and that's that in statistics, a sequence of estimators, and we'll deal with what estimators are more in Math 445, but they're going to be random variables that tell you how you might estimate a quantity of interest, a parameter of interest. So we have this sequence of estimators for an unknown parameter p, and that's going to be called consistent if our estimators converge in probability to the true parameter that we're trying to estimate. And consistency is a very good property that we're concerned with in statistics. So these are the four remarks that I really want to make regarding the weak law of large numbers. And so now I think it would be good to move on to an example so that we can grapple a little bit with how we might apply this and what that might look like. Now, this next example I am going to leave a lot to you in order to verify, but that should help the result be ingrained a little bit more. And so with this example, we're going to be investigating the sample variance. So again, we're going to be working with a sequence of IID random variables. And the reason that we're working with the sequence is that we want to be able to work with any size n we want to. And we're going to be working with a sequence, so we're going to let that be a sequence of IID random variables with, again, expectation equal to mu and finite variance equal to sigma squared. And so we need a definition before we begin, and that definition is going to be for the sample variance. And the sample variance, let's give it some notation. So let's let that be s squared sub n. That's a capital S so that we know that it's a random variable. And this is equal to 1 over n minus 1 times the sum from I equals 1 to n of the squared distance between xi and x bar n. And so this is a very commonly used estimator of the variance in statistics, but let's see why we might want to use that. And so let's first ask ourselves, is this sample variance a consistent estimator of the population variance, sigma squared? And so we know that we need to show if this thing is a consistent estimator, then what we're going to need to show is that the sample variance converges in probability to the population variance. So that is, we need to show that sample variance converges in probability to our population variance. Okay, so where can we start here? First of all, we're going to need to deal with an epsilon. So let's let epsilon be greater than 0. And then let's start off like we did before. So we're going to start off with the probability of the absolute distance between our sample mean and the sample variance, and the population variance. I'm going to let that be greater than or equal to epsilon. And then what we can do here is jump using Chebyshev's inequality to the fact that we know that this is going to be less than or equal to the variance of the sample variance divided by epsilon squared. And so that's going to be by Chebyshev's inequality. And something else we need to think about, and you might be asking yourself, well, what's going on here exactly, and why can we apply Chebyshev's? Well, if you think about what we'd have to talk about is that, well, we'd have to show that sigma squared is equal to the expectation of the sample variance, and that is true. So the expected value of the sample variance is equal to the population variance, which is why we can apply Chebyshev's inequality. And I'm going to leave that derivation to you. So you should be able to do that using all of the tools you've learned so far in probability. And so now that we're here, we can move on to where we want to be. So we can start off by saying, well, this is the probability that the absolute distance between the sample variance and the population variance being less than epsilon, well, that's going to be greater than or equal to 1 minus the variance of the sample variance divided by epsilon squared. And so what we're going to see is that in order for the sample variance to converge in probability to the population variance, we need the variance of the sample variance to approach 0 as n approaches infinity. And I'll leave that to you to verify. Now that we have discussed the weak law of large numbers, we need to turn to the strong law of large numbers and see how that actually differs. What I will prompt this discussion with is that we can't really deeply investigate the strong law of large numbers using everything we've learned in this course. It requires a little bit more, and so an investigation of the strong law of large numbers is something I'll leave to graduate study or maybe an independent study later on. But for now, it is interesting to see how these two things differ and how the strong law of large numbers grapples with those strings of bad luck we talked about in the coin flip example. So let's first start by stating the strong law of large numbers, which I will not give a proof for. And the abbreviation I use here is going to be SLLN. And what the theorem says is that if we let x1, x2, ... be a sequence of IID random variables with expectation of xi equal to mu and finite variance of sigma squared, then for all epsilon greater than 0, the probability of the limit from as n approaches infinity of the absolute distance between the sample mean and the population mean being less than epsilon is equal to 1. So now you can stare at this for a little bit, and what you might start to think of is pointwise convergence, and that is something that I would certainly encourage you to think about and draw the parallels between the strong law of large numbers and pointwise convergence. Of course, the probability statement makes it look a little bit different, but it's still a good exercise. So now let's just focus on some remarks that'll help us grapple with the strong law of large numbers. The first remark I'll have is that this is another mode of convergence. So this form of convergence is called, in probability, almost sure convergence. And we use the notation, and again remember that the notation I'm going to be using here just has some random variable approaching its mean. So here I'm using x bar and the sample mean as my random variable, and we just write AS over that arrow to denote almost sure convergence. Okay, and so now let's see what the strong law actually says. Well, the strong law of large numbers says that the sample mean converges to the population mean with probability 1. And so what does that actually mean? Well, if we think back to our coin flip example here, this means that the set of possible sequences of heads and tails that started to pull the sum away from 1/2, well, those types of strings have probability 0. So if we go back to when we say almost sure convergence, we mean almost sure is that it does converge everywhere that has probability non-zero. So the places where we think that the sample mean, or that not that we think, where the sample mean doesn't converge to the population mean, well, those areas, those situations have probability 0. And so that's what the strong law certainly says. The last comment I have is that almost sure convergence is stronger than convergence in probability. So it's a stronger form than convergence in probability. And so what this means practically is that if you have a random variable that converges almost surely to its mean, then you know that that random variable converges in probability to its mean as well.